So I'm Matthew, but this is joint work with a bunch of collaborators: Stanley Wu, John Ullman, Roxana Gambasu, and Alina Oprea. I'm particularly happy to mention that Stanley Wu, the joint first author on this paper, has accepted a PhD offer at University of Chicago. So I hope that you all will look forward to his work. So machine learning models these days are being trained on private data. I think we're all comfortable with this in the room, or we're all aware of this. Models are being trained on things like emails, medical images, text messages, and when you train machine learning models on private data, you run the risk of those models leaking private information as well. So the type of leakage that we're going to be considering in this talk is known as membership inference. The goal of this adversary in membership inference is to learn whether a given target record is contained in the training data set of a model or not. This was originally designed for sort of genetic data releases back in 2008. This attack was first proposed then, but the machine learning privacy community adopted it like 10 years later, and we've been using it ever since, and it's essentially the most widely studied attack on machine learning. So that's why we look at it here. This talk specifically considers the model update setting, where you repeatedly update a model over time. So you can think of this, you originally collect your nice data set, you train a good model, but over time maybe you find that you can collect more data, or the distribution drifts in some way, and so you want to collect more data to keep your model fresh. And so what you do is you collect new data, you update that model. So here you're going from F0 to F1, and you maybe do this thing a couple times, and so essentially you get this sequence of models. And the question that we're asking in this paper is, does having access to this sequence give you better membership inference attacks than having access to just one of the models? This isn't a new question. There's been a couple works that look at this. They do a bit of different things, but in this talk I'll be focusing just on some sort of things that we do that are new. But I just want to highlight that at CCS 2020, Zinaya Bagayin et al., they show that if you're looking for secret exposure, a different kind of attack, this can be improved on NLP models. You can do data reconstruction. This was shown in a Usenix 2020 paper by Salem et al. And in sort of the reverse procedure of model updating, machine unlearning, instead of adding, you're deleting data. You can also improve inference attacks. This is something that was shown at a CCS 2021 paper and a PETS 2022 paper. In this talk, I'll be just going over some things that are different from prior work. To start, I'll just talk about a game that we propose. I'm not going to go into the sort of formality of the game, but you'll sort of get an idea for how it differs from the standard membership inference attack setting. And then I'll talk about how we actually do our attacks on updated models. And then I'll talk about two little sections of the paper that I think I personally like, where you can repeatedly update a model, what you can learn extra in that setting, and also what happens when you train with differential privacy. So I'm going to start with the sort of standard membership inference attack setting, where essentially you have a model that's collected, you have a data set collected D1, you train a model F1, and your goal is to learn whether this target record is in D1, right? So this is the standard membership inference setting. You can construct a privacy game to model this setting. And in our work, we sort of simply extend that to, you have two data sets, D0, D1. You train these two models, and you give the adversary access to both of them. So this is the sort of very natural adaptation of the standard membership inference attack. And we also have a couple different variants of our privacy game that extend it to with the multiple update setting like I showed before, or to accommodate distribution shift, which often happens when you're updating models. And you can do that just by sampling D1 in a different way. So once you have access to both of these models, the question is, what do you do? The thing is, we didn't want to come up with a new attack because membership inference attacks are a really hot area of research. And so what we decided instead is let's start from a membership inference attack. This is a whole line of research. People have come up with all these different ways of doing it, and essentially every way computes something like a privacy score. The higher the privacy score, the more likely the adversary thinks it's contained in the training set. And there's a ton of different metrics like this. The state of the art, I think, like 2 weeks ago was something, and now it's something else. And so it's updating all the time. But the idea that we're going to take advantage of is we're just going to use those, and we're going to combine them on F0 and F1, and we're going to just use that. And so we have these two different, very simple ways of combining. The idea is that once you pick a membership inference attack, and maybe once someone comes up with a better membership inference attack, you can use that instead and then improve your updates. And so actually, we showed this at the time that we originally wrote this paper. We used a simple attack, and then a new state-of-the-art attack came out, and it improved our results. We also have some theoretical discussion of this. I personally like it a bit, but it's a little bit too much for the talk. So you should check it out in the paper. One thing that you can do that's kind of cool is something called entry inference when a model is repeatedly updated. So if you think of membership inference as asking, is an example contained in the training data set? Entry inference asks, when is an example added to the training data set? And the harms here that you can think of for membership inference and entry inference are not necessarily correlated, right? So if you think of like maybe the standard motivation for membership inference is something like you're included in a medical data set, and your membership leaks some medical information, like that you have a disease. You know, maybe also when you caught the disease or something could also leak information that you don't want someone to know. But there's also cases where membership inference is risky, but entry inference, it doesn't seem so much. So for example, if membership inference leads a social security number that you typed in a text message to be learned by a model, that's really bad. But entry inference would leak when that social security number was written, which, it's really the content of the message that matters here. But there are also cases where entry inference maybe matters more. So if you went to a specific cafe, maybe isn't so risky. But when you went to a specific cafe, might leak who you met with there, and you might not want people to know that. So these are two distinct risks. But what you can do is actually you can construct an entry inference attack that essentially takes membership inference, and this is sort of what we did in the paper. So you can start with this membership inference, and you want to learn, is this target record in D1 in the first model update? And so what we saw earlier is that to do this, you compare F0 and F1. And so now you have some score measuring how likely you think it is that this target record is in D1. And then you just do this again for D2, comparing F1 and F2. You keep doing this for all the model updates you have access to, and then you just pick the one with the highest score. And this turns out to work pretty well. I'm not going to actually get into any results, but you can check the paper for that. Because I want to get to this last piece, which is near and dear to my heart. And all you need to know in this slide is that differential privacy is this thing that uses a parameter called epsilon. Epsilon essentially provides an upper bound on any privacy attack, almost all privacy attacks, but including membership inference. And something that you can do is then, because epsilon upper bounds the attack, if you have an attack that lower bounds like the sort of epsilon value. And so you can do things like run attacks to see if you have a bug in your privacy implementation, how much your privacy proof can improve, or just to get a better sense for the empirical values of privacy that are protected for a given epsilon. And so when we run this on our attack, we actually get pretty good results. Really, all you need to know here is that this gap between the upper bound, the provable upper bound, and the lower bound that you get from the attack is something like 2 to 4 in this range of epsilons. And that probably doesn't mean anything to you, but in the attacks that do this for training from scratch, it actually takes quite a lot of work to get like a factor of 10. And so here we're finding that this update setting really, when you train with DP, is empirically much less private than what you might get from full batch from scratch training. With that, I'd like to thank you for coming. We talked today about how membership inference attacks can be improved in the model update setting. You can learn when someone enters a data set if the model's repeatedly updated, and you get nearly tight attacks on DP training. There's some other cool things I think in the paper, like our theoretical results, some comparison to prior work, and what happens when you have distributions that shift. But I'm happy to take any questions now.
So let's thank our speaker. And yeah, let's go for questions from the audience.
Yes, thank you very much for the talk. I would be interested if you have a higher attack success if there's indeed a distribution shift. So let's imagine the data that you update the model with is very similar to the original training data, or it's very different. Like, does it make a difference on your attack?
Yes, thank you for giving me an opportunity to talk about this. It does happen. It kind of depends on how the drift happens. But yeah, we have some results where if it is a very drastic drift, those points that sort of lead to the drastic drift do get leaked much more. Thanks.
You didn't coordinate, right?
No.
Further questions?
Thank you for the talk. My question is, when you do inference entry, like you're looking at a particular point, you want to see where it entered, you're sort of searching for doing multiple hypothesis tests, one after the other. This usually in statistical hypothesis testing, this usually constitutes a problem where your false positive rate sort of blows up as a result. Did you observe something similar, or do you have a way to combat this?
Yeah, so we didn't do any like explicit correction for like statistical stuff, except for in the DP world. But I guess like the thing that we observed is that essentially the more updates you have, right? Like if you have 10 updates versus 2 updates, it's sort of like a 10-way classification problem instead of a 2-way classification problem. And so we do observe that the accuracy does decrease as you have more and more updates, but sort of the improvement over random guessing actually increases significantly. So it's like a more modest decrease than you would expect, just given that you're making the classification problem harder.
Okay, further questions? There was one here, I think.
Thank you for the talk. I was just wondering how different this setting is from federated learning attacks, which have also followed a similar setting, where there are individual data sets and clients repeatedly receive updates. So I was just wondering what's the difference and whether this attack can be applied in a federated setting as well.
Yeah. I guess you could do this. I mean, I guess there's different sort of assumptions and whatnot in federated learning, a different adversary power. So you could imagine maybe being able to do a lot more in federated learning. And indeed, I think the results so that you can. The results of other papers on federated learning attacks.
Thanks, Matthew, for the great talk. I was also curious that in your case, you assume that you have access to all of these models, F0, F1, and so on, right? What if you have only access to a single model, for example, like F10? Can you also, like, for example, quantify when the given data point was added? For example, you have like weaker signal from, let's say, data points that were in D0, D1, and so on, and very strong from, let's say, D10.
Yeah, so I mean, if you only have access to one of the models, then kind of the best thing you're going to be able to do is just like a standard membership inference attack, right? If you have access to a couple, like you're going to get some granularity and you'll maybe learn like it was added from this time to this other time much later. But yeah.
2 comments from authors in the session. Maybe we should just go away with presentations and make all sessions panels. It'll probably be a lot more fun and a lot more engaging. But we also have online questions. So why does the lower bound, upper bound gap change with varying epsilon values?
Yeah, there's a lot that kind of goes into this. Like at a very, very low epsilon, your model essentially doesn't learn anything from the data, and so privacy attacks don't really do much. You also have to sort of correct for things like statistical error, because attacks are an empirical thing and differential privacy is a provable thing. And so those things actually really hurt at the low epsilon values. And at the high epsilon values, you need a basically perfect attack to do anything with that. So it's a bit of a technical detail, but you can look at some of the prior papers to understand more.
So thank you. Please join Zulip and answer the further questions there. And let's thank our speaker again.